Welcome back to our discussion about the absolute maximum and the absolute minimum of a function of one variable. We had defined the concept of absolute maximum and the absolute minimum. So, the point of absolute maximum is the point where the function takes the largest value in the domain of the function, and the absolute minimum is the value of the function at a point where the value of the function is the smallest as compared to the value of the function at all other points in the domain of the function. That is why it is called the absolute maximum and absolute minimum. And we have said that to locate the possible points where the function can have absolute maximum or absolute minimum is same as that of local maximum and minimum, because absolute maximum is also a point of local minimum. So, we collect together all the points possibly where the function is not differentiable in the domain of the function, and look at the points in the interior points in the domain of the function where the derivative is equal to 0. This is the second set of points, and the third set of points is the points which are the end points. For example, the domain could be a interval and closed interval, or and the end points of that interval are possibly also the points where the maximum value of the function can occur. So, among these three set of points which are same as that of for analyzing local maximum or minima, one locates these points, compares the values of the function at these points and see which one is the largest and which is the smallest. And of course, the critical point or the crucial point in this analysis is that the function should have absolute maximum and absolute minimum. And the only theorem that we have discussed and stated is what is called the max-min theorem for continuous functions on closed bounded intervals. So, that said that given a function on a closed bounded interval, if it is continuous, then it will always have a point of absolute maximum and a point of absolute minimum. So, whenever we do problems in our discussions, one should ensure that the functions involved are all continuous functions. So, let us look at some examples. So, let us look at the example where the function is given by f of x is equal to minus x if x is between minus 1 and 0, and it is equal to 4 x minus 2 x square if x is strictly bigger than 0 and less than or equal to 2. So, the function is defined differently for the values minus 1 to 0, and it is defined differently for values bigger than 0 and less than or equal to 2. So, this function is defined that the domain of this function is the closed bounded interval from minus 1 to 2. So, the function is defined in a closed bounded interval minus 1 to 2. Is it continuous? Let us analyze. Look at the function in the interval minus 1 to 0, at all points it is minus x, which we know is a continuous function. Also in this interval, the open interval 0 and closed at the point 2, it is defined by this quadratic function. So, which we know from our illustrations, discussions in continuous functions that this is a continuous function. So, the only point left is the point x is equal to 0. Is it continuous at that point? To find that, one analyzes the left limit at the point 0 and the right limit at the point 0. The left limit at the point 0 will be found by taking a sequence x n converging to 0 from the left side. That will give you f of x n as minus x n, and x n goes to 0 implied the left limit exists and is equal to 0. Similarly, if we take the right, want to compute the right limit of the function at the point 0, we will take a sequence coming to 0 from the right side. That means, this is the value of the function. So, if we take a sequence x n converging to 0 from the right, then f of x n will be equal to 4 x n minus 2 x n square. As x n goes to 0, 4 x n will go to 0 and 2 x n square will also go to 0, because x n goes to 0. So, using the fact about limits, limit theorems for sequences, we will see that the right limit of this function at the point 0 is also 0. So, this function is continuous in the closed bounded interval minus 1 to 2. So, this will have a absolute maximum and absolute minimum in that interval. So, that is ensured. Now, the question is to find out what is the value which is the absolute maximum and the absolute minimum, and how do you find that. So, to do that, let us look at the function in the domain -1 to 2. We first of all claim that f is not differentiable at x is equal to 0. So, how do you prove that? So, that it is not differentiable at x equal to 0. So, let us analyze that by working out the derivative from the left and the derivative from the right. So, let us look at, I want to find out derivative at the point 0 from the left side. So, that is equal to limit f of, I want to go to the limit. So, let us like 0 minus h minus f at 0 divided by h going to 0 and h bigger than 0. So, that will ensure f of 0 minus h. So, that means h is positive. So, you are on the left side of 0. So, what is this quantity? This is equal to limit h going to 0, h bigger than 0. So, what is f of 0 minus h? On the left side of 0, the function is f of x is equal to minus x. So, it is minus h minus f at 0 is 0 divided by the value h. So, this and that is equal to limit h going to 0, and this when you divide, this is equal to minus 1. So, this limit equal to minus 1. So, the left hand derivative of the function at the point 0 is equal to minus 1. Let us compute the right hand derivative of the function at this point. So, let us compute the right hand derivative. So, we want to compute f dash at 0 plus. So, that will be equal to limit h going to 0 of f of 0 plus h minus f at 0 divided by h positive. Again h is positive, but here I have written 0 plus h. So, that means you are on the right side of the point 0. So, let us put the value. So, that is limit h going to 0, h bigger than 0. What is the value on the right hand side? The function is defined as f of x is equal to 4x minus 2x square. So, this is 4h minus 2h square minus the value at 0 is 0 divided by h. So, that is equal to limit h going to 0 of 4h square minus h. So, this h cancels with this h and one power cancels with this. So, it is 4 minus 2h, h going to 0, h bigger than 0 of course, and this limit we know h is going to 0. So, that is equal to 4. So, the left hand derivative was equal to the left hand derivative of the function was minus 1, the right hand derivative is equal to 4. So, f dash minus at 0 is equal to minus 1, which is not equal to 4, which is equal to f dash the right hand derivative at 0. So, implies that the function is not differentiable at the point x is equal to 0. So, that is how you analyze the differentiability of a function of one variable if it is defined differently from the left and differently from the right. So, it is always good to work out these things. So, f is not differentiable at the point x is equal to 0. Now, at all other interior points we have to find the derivative and put it equal to 0. So, we saw that this is left hand derivative is minus 1 and the right hand derivative is equal to plus 4. So, that is fine. So, now let us look at the derivative. The function was defined minus x in the interval minus 1 to 0. At 0 we are discarding because that is the point of non differentiability. So, in the open interval minus 1 to 0, the function is minus 1. So, it is differentiable at the point minus 1 and the derivative is equal to minus 1. And at the point in open interval 0 to 2, the function was defined as let us go back and look 4x minus 2x square. So, in the open interval 0 to 2, the function is again differentiable and derivative is 4 minus 4x. So, let us put these values that so the derivative function is minus 1 for minus 1 less than or x less than 0, and it is equal to 4 times 1 minus x if x is between 0 and 2. So, to find out the points where the function can have a maxima or minima, we have to put it equal to 0, and of course, derivative between -1 and 0 is -1. So, the function cannot have any point inside that interval. Only in this interval 4 into 1 minus x is equal to 0, that gives you the value, namely x is equal to 1. So, the possible points where the function can have local maxima or minima and absolute maxima or minima are what we call as the critical points, and these points are the end points. So, -1 and 2 are the end points. So, -1 and 2 are the end points. 0 is the point where the function is not differentiable, right, interior point, and the function is not differentiable, and the point where the function derivative exists, interior points and derivative is equal to 0. So, these are the four points where possibly where the function can have absolute maxima or minima, and these will be out of these only because of the necessary condition for maxima minima. So, what we do is find out the values of the function at these 4 points and compare them. So, let us find out the values. F at -1, the -1 the value was minus right, at -1 the value is equal to minus x. So, the value is equal to 1. F at 0 is 0, f at 1 is 2, and f of 2 is equal to 0. So, these values are computed by looking at the expression of the function which is given to us. So, let us go back and look at the function. So, function was this. So, at the point -1 the value is 1, at the point 2 you put x is equal to 2 in this. So, you compute 4 into 2 is 8, 2 into 2 4 is 8, that value is equal to 0. In between point was 0 and 1, at the point 1 the value is -1, at the point 1 the value is 4 minus 2, that is 2, at the point 0 the value is 0. So, let us compare these values. So, we found out these points, and the values at these points were f at -1 is 1, f at 0 is 0, f at 1 is 2, and f of 2 is 0. So, among these 4 possible values, the largest value is 2. So, the function has absolute maxima which is equal to 2, and the point of absolute maximum is x is equal to 1, and the function has absolute minimum, that is 0, and the points are 0 and 2. So, at 2 of the points the function has absolute minimum and maximum at the point 1. So, this is how one analyzes absolute maximum and absolute minimum of a function. So, once again the strategy is, first of all, given a function, ascertain that it will have absolute maximum and minimum or minimum by looking at the domain of the function and analyzing the continuity of the function. So, the theorem that a function defined on a closed bounded interval which is and the function being continuous will give absolute maxima or minima, will ensure. And then we go through the process of, as we do it for local maxima and local minimum, we look at the points, could be end points, could be the interior points where the function is not differentiable, or the points where the function, interior points where the function is differentiable and derivative is equal to 0. Let us look at an example of finding absolute maxima minima as in a problem in economics. So, consider a linear output model given by q is equal to 100 minus p. So, here p is output, or you can think of it as a demand. So, this means that when p is bigger than 100, this quantity will be negative. So, this does not make sense at all. So, that means there is no product when the price exceeds 100 or more. So, let us assume that the cost for q is 25 q. So, cost of producing q units is 25 times q. So, with this let us find the total revenue. So, as we know, total revenue is the price into the quantity produced. So, p into q. So, 100 minus p multiplied by q. From here we have to find the price of p. So, p is taken on that side. So, it is 100 minus q. So, so the P into Q is equal to 100 minus Q square. So, total revenue will be this is a typo here, it should be 100 Q actually, P into Q. So, P is equal to 100 minus Q. So, it is 100 Q minus Q square. So, the total profit is given by total revenue minus the total cost. So, P times Q minus CQ. So, that is the total revenue minus the total cost. So, that is P is equal to as before 100 minus Q square and CQ is 25 Q. So, that gives us 100 Q minus 25 Q, that gives 75 Q minus Q square. So, that is the total profit function, and to find out the possible points where it can have maxima or minima, first of all we find this is defined for all values of Q bigger than or equal to 0. So, let us analyze what is it is a differentiable function. So, what is the derivative? So, the one would like to maximize. So, let us find out the derivative. So, the derivative is equal to 100 minus 2 q. So, from here, or it is 75 minus 2 q. So, that gives us the value of q equal to 37.5. So, at the when the number of when the q the output is 37.5, the profit will be either maximum or the minimum. We do not know, one has to analyze what will be the nature of either apply the first derivative test or the second derivative test. One can apply here the first derivative test if you like. So, it is 75 minus 2 q. So, second derivative is equal to minus 2. So, the function will have a maximum at the point q equal to 37.5. Now, the question comes, is it absolute maximum or not? Of course, the function is continuous, but we do not know, the domain is not a closed bounded interval. So, what we know is surely there is only one critical point. So, we can close the domain of the function after any point q 37.5. So, we can imagine our function, because we know that there is only one critical point. So, there is only one possible value where the function can have a local maxima or minima or absolute. So, we can imagine the function mathematically to be defined in the closed bounded interval, say 0 to say 40 if you like, and then say it is in the closed bounded interval 0 to 40. So, it must have an absolute maximum or minimum in that portion. And since the second derivative at this point, second derivative everywhere is minus 2. So, this q equal to 37.5 is a point of maximum value and is the only maximum value the function can have. So, the endpoints are 0, and if you look at one can think of saying at the point 40, right, q is equal to 40, what is the probably that is that the value to be considered for absolute maximum or not. So, one can look at the nature of the derivative. See, on the left of the derivative, on the left side of this, the function is derivative is positive. So, it will be increasing, on the right side it will be decreasing. So, after 37.5 the function is going to decrease. So, no value bigger than 37.5 is going to occur. So, we conclude from all this discussion that the second the function has absolute maximum, local maximum, and hence actually absolute maximum at the point 37.5. So, what is the profit price, maximizing price for the company? So, that we put in the P is equal to 100 minus q. So, q is equal to 37.5, that gives you P equal to 62.5 as the maximizing profit, right. So, and the maximizing profit is the price at which maximum price at which maximum profit can be made is this, and the maximum profit will be putting that value q 0 in pi q, the profit function, and that gives you this value. So, this is the graphical representation of all the information that we have done till now. So, look at this blue function. that is the profit function 75q minus q square. This red line is the cost function C is equal to 25q, that is a linear function, so graph is a straight line. The profit function is quadratic, so as the graph is going to be like a parabola, and q, the coefficient of q square being negative, it is going to be parabola like this. And similarly, the total revenue is again a quadratic with the negative sign of q square, so it is again going to be a parabola. Right. So, this is and if you look at the maximum the quantity q output where the maximum value occurs, so maximum profit is at this point and my maximum revenue of course will be at this point. And now, here is a observation that we should keep in look at on the in this side of the graph. This is the price demand function. So, there is a blue one, this is the price demand function, and there is the marginal of the revenue, green one is the marginal of the revenue. And this marginal cost is this red line, that is the marginal cost. So, that marginal cost meets the marginal revenue at this point B. So, that means this is the point where the marginal cost will be equal to the marginal of the revenue, and that actually is happening because that is a 0.37.5. So, one can also see it in the scenario of the graph. See, this is the cost function. So, if we want to say that the revenue at the point where there is a maximum, the marginal is equal to the slope of the marginal is equal to slope of this line, the total cost. That means, the tangent at this point will be parallel to the line marginal cost, because that is linear. So, that is also indicated here. So, this is how one can interpret graphically the data. So, we are verifying in this example that the marginal cost, right, marginal of the cost at the point of maximum output is same as the marginal of the revenue at that point. So, that is graphically illustration, and we had already checked it by mathematical formulation of that. So, this is what we can check on the graph, that the marginal of the revenue is same as the marginal of the cost. So, today what we have done in this lecture is try to look at the absolute maximum and absolute minimum, how to find absolute maximum and absolute minimum, and apply it to some of the examples in economics. So, we will continue this study next time. Thank you.